Hey everyone, welcome back. Today's video is for anyone who may be interested in learning how to program in assembly language, but may not know exactly where to start or exactly what's involved in terms of what knowledge we need and what tools we need to begin programming in assembly language. So today we're going to be covering a lot of different aspects that we need to keep in mind before we begin learning to program in assembly language. So I think it'll be a good place for us to start to really give us an idea of what all is involved in that process. For example, if you've ever programmed in BASIC, you're probably aware that it's pretty simple to start programming in BASIC, particularly on a retro computer, which often have BASIC already installed, or it may come on a separate cartridge or on a disk. They also will often include a user manual, which has instructions on exactly how to begin programming in BASIC, which makes it very easy. But with assembly language, that's not the case. Assembly language involves a lot more in terms of knowledge as well as tools that we need in order to begin programming in assembly language. Although today we're very fortunate that we have a lot more advanced tools available for us for programming in assembly language, so we don't actually have to program on the actual native hardware, which is these old retro computers. So if that all sounds interesting to you and you may be interested in learning assembly language, but you're not sure exactly where to start, then stick around and we're going to take a look at these considerations right now. All right, so we'll go ahead and get started here, taking a look at the different considerations and different topics we need to be familiar with when learning to program in assembly language. And we're going to be covering these four topics here: the different considerations, different areas of knowledge, different tools we need, as well as some considerations for actually designing our assembly language programs. So let's go ahead and get started here. And our first slide is titled Computer. So obviously there are several different computers we might be interested in programming in assembly language. There are, for example, as shown here, Spectrum computers, Apple computers, Aquarius, Atari, etc. It's useful to know which computer we're interested in programming for, so that, as we'll see on a later slide, we can familiarize ourselves with the different aspects and characteristics of that computer, and it will give us a good starting point when beginning our assembly language programming journey. All right, so we'll move on to our next slide here, which is titled CPU, which is Central Processing Unit, or Microprocessor. So it's important to know what microprocessor our computer has before we begin learning assembly language programming. For example, is it an 8-bit, a 16-bit, or 32-bit microprocessor? And this term typically refers to the size of the registers inside the processor and how much data each register can store. But there are also some other considerations that refer to 8, 16, and 32-bit, which are the address, data, and control buses that are shown in point 3 here. Now, if we go back up to point 2, which says speed, it's important to know what speed our processor is running at, because each assembly language instruction requires a certain number of clock cycles to execute. So if we're interested in finding out how long it's going to take our program to run, how long it's going to take each program instruction to execute, then we need to know the speed of our processor and how long it takes each cycle to operate. So we don't necessarily need to know exactly how fast our processor is running unless we're particularly interested in maximizing the speed of our program. But if we are interested in maximizing the speed of our program, then it's useful to know how fast our processor runs, and then we can figure out how long our program will take to run based on how long each instruction takes to execute. All right, we'll go down here to point number 4, which is titled Interrupt Modes. So different processors have something called interrupt modes, and they might have different types of interrupt modes. And this is important when you're programming in assembly language, because since assembly language is such a low-level programming language, we're programming almost at the level of the actual hardware itself. And if the chip or the CPU or the microprocessor has interrupt modes, it's helpful to know what type of interrupt modes it has and how they operate. So why would we be interested in what the interrupt modes are for our particular processor? Well, this would be important if, for example, we're going to be wanting to enable and disable the interrupts. There might be certain points in our program where we want to, for example, disable the interrupts and then re-enable them again later. We may want to write an interrupt handling routine to handle an interrupt, depending exactly what type of system we're programming for, or we might want to make use of any existing interrupt handling routines that are already built into the ROM of the particular computer that we're using. So it is useful to know about the interrupt modes that our particular processor supports. And then our last point here is labeled assembly instructions. Now, obviously, every processor has its own different set of assembly language instructions, and of course, we're going to need to be familiar with those instructions and how they operate in order to be able to create assembly language programs. All right, so let's move on to our next slide, which is titled Computer Architecture. And over on the side here, we have 3 points: CPU, memory, address data control lines. So typically a microcomputer would consist of at least these 3 different types of items: the CPU, which is the processor we just looked at, the memory, which consists of ROM memory, RAM memory, and the different ways that memory is split up and how it's used, as well as the address data and control lines, which are called buses. As shown here in the diagram, we have an address bus, a control bus, and a data bus. So it's good to be familiar with at least a general understanding of how the computer architecture works and how the processor and the memory and these control buses all work together to make the computer operate. Okay, our next slide is titled Number and Counting Systems. So when we're programming in BASIC, for example, which is a high-level programming language, we can pretty much do all of our counting in decimal. We can just enter regular decimal numbers into our BASIC program and it will work. However, with assembly language, we need to also be familiar with these other 2 types of counting systems, which are binary and hexadecimal. And so if we take a look at the regular decimal examples I've shown here, for example, I've got the number 255 and 65535 listed here. And if you're familiar with binary arithmetic and bits and bytes, you're probably familiar with these 2 values because they are the maximum values that can be stored in 1 byte and 2 bytes respectively. Now these would be unsigned values, so these are positive values, whereas if you're using signed arithmetic, then it would be different. For example, 1 byte in signed arithmetic could store values ranging from minus 128 to positive 127. So it's very useful to be familiar with the counting systems that are involved with our microcomputers, being decimal, binary, and hexadecimal. So for example, if we take a look at our binary example here, the first one is a byte, which is a string of 8 bits stuck together. And as you probably know, a bit can have one of 2 different states, being either on or off, represented by a 1 or a 0. And that byte can be further broken down into nibbles, which are groupings of 4 bits. And each grouping of 4 bits, which is called a nibble, is also going to be useful when we take a look at our hexadecimal counting system in a moment. And then finally down here we have 2 groupings of 8 bits, which is 2 bytes, which is called a word. And that allows us to use larger values when we're counting. So let's take a look finally down here at the hexadecimal section. Hexadecimal is very important to be familiar with in assembly language. And you can see here there's a couple of examples. The top example here uses 2 digits, and each digit represents a nibble, which is 4 bits. So this 5 digit represents these 4 bits here on the right, and the A digit represents the 4 bits on the left. So 1 byte of data can be converted to 2 hexadecimal digits, with each digit being equivalent to a nibble, which is 4 bits. And as you're probably familiar, hexadecimal is a base 16 counting system, which means that each individual digit can have one of 16 different unique values, ranging from the character 0 through to the character F in this case. And down here finally at the bottom, we have 2 bytes represented in hexadecimal. And again, each character represents a nibble, which is 4 bits. So we need to be familiar with all 3 of these counting systems: decimal, binary, and hexadecimal, when we're using assembly language. And let's take a look at these points I've listed on the right here. The top one being able to convert between formats. So obviously it's going to be very useful for us to be able to convert between these different counting formats when we're using assembly language, so that we know how these numbers are represented in our program. For example, in the program listing, they might be represented in hexadecimal, whereas in our program, we might be more interested in the binary form of a number when we're looking at bitwise operations, for example. So we need to be able to convert between these three different formats. And of course you can use a calculator to help you do that, a programming calculator, but it's also very useful to be able to do that manually and really understand the relationship between these three counting systems. And again, for my second note here, it says able to count in each counting system. So in addition to being able to convert between these three counting systems, we also need to be able to understand how to count in each of these three counting systems and where exactly each digit rolls over to its next value and how the carries work between one digit and the next. So it's important for us to be able to count in each of these systems as well. Our third point here says byte/word value limits. So as we mentioned briefly at the top here, in decimal, these two values represent the limits that a single byte and 2 bytes can hold in decimal. So it's important to understand exactly what values can be held in each of these three counting systems for a particular size of number, whether it's a single byte or a double byte, whether it's a word or a nibble. So we need to understand exactly the limits of what values can be stored in each of these three counting systems as well. And then finally, our last point here says bit operations. So this is a lot different than using decimal numbers in BASIC, for example. In BASIC programming, when we're using decimal numbers, we typically use them with regular arithmetic operations that we're familiar with: addition, subtraction, multiplication, division, and so forth. But with assembly language, since we're very interested in the binary versions of these values a lot of times, we have something known as bit operations, where we can actually check and manipulate the individual bit values within a byte. So that's not something that exists in BASIC, but it is something that is very prevalent in assembly language, and we need to be familiar with the bit operations for these different values as well. All right, let's move on to our next slide, which is titled Development Toolchain. So as I mentioned earlier, when you want to program in BASIC, for example, which is a high-level language, there really is no development toolchain that you need to install and configure, because a lot of times these retro computers come with BASIC pre-installed, and all you have to do is turn on the computer and possibly insert a cartridge or load BASIC from a disk. But other than that, that's pretty much your toolchain. Now, of course, if you're programming in BASIC on a modern system, you might not necessarily want to create your BASIC program on the actual native hardware, which is the old retro computer. Although you can do that, you may prefer to use more modern tools. For example, you might want to create your BASIC program on a PC and then convert it to a program that can run on the native hardware. But generally speaking, creating a BASIC program is very simple, and it requires a very simple toolchain. Now, when we're looking at creating an assembly language program, then the toolchain is a bit more complex, and we require all of these different tools that I've listed over on the right side here. For example, the first point says editor. So this would be someplace where we can actually physically type in our assembly language program. And the next point here, which says assembler, is the tool that will assemble our assembly language program into machine code, or convert it from assembly language into machine code. And oftentimes you will find these two tools combined together in a package, which is called an integrated development environment, or IDE, which I covered in my previous video, where we looked at the Aqualite IDE. And in my other previous videos, I've also looked at another integrated development environment called Spin for creating programs for the Sinclair Spectrum line of computers, for example. But oftentimes the editor and the assembler will be combined in a single integrated development environment. The next point I've listed here is a debugger, which helps us to debug our programs and troubleshoot our assembly language programs. Now, the fourth point here is an emulator. So this is important when we're developing programs not on the native hardware, which we typically wouldn't be doing with assembly language. So for example, if you're programming an assembly language program using maybe a Windows PC, then you would need to actually run that program to test it out somewhere. And the two ways we could do that would be to save it on some sort of media that we could run on the native hardware. For example, we might save the program onto a cassette tape somehow and then load that on the hardware. Or if we have a more modern version of the computer that has an attachment that allows us to maybe connect an SD card or a USB stick, then we could save our program onto that media and run it again on the native retro computer. However, if we want to run the program on our modern computer, on our PC or our Mac or our Linux box, Then we would use something called an emulator, which emulates the operation of the actual retro computer we're interested in programming for. And this will often come installed as part of an integrated development environment as well. All right, so the last 2 points here that say graphics and sound, these would be tools that we would need even if we're programming in another language such as BASIC, for example. We might find it useful to use specialized tools to allow us to design our own graphics and design our own sound effects and music. So those are tools that are not absolutely critical in creating an assembly language program, but they would be helpful in, for example, creating a game that we want to make for our computer. All right, let's take a look at our next slide, which is titled Assembler Directives. So we mentioned earlier about the assembly language instructions themselves that are related to a particular processor. So each processor or CPU understands a certain list of assembly language instructions. And this is what we would use, obviously, to create our program. But as well as being familiar with assembly language instructions, there's another very important and very powerful set of instructions that we need to be familiar with when making an assembly language program. And these are called assembler directives. So when we create our assembly language program, we type it into an editor, and then that program gets converted to machine code using an assembler, which, as I mentioned before, may or may not be actually built into the editor, depending on what development environment we're using. But regardless of how we exactly put together our toolchain and how the editor is related to the assembler itself has operations that are very valuable to us. And these are operations that take place when the assembler converts our assembly language program into machine code. So this is different from a basic program, which gets converted to machine code on the fly while it's running using a basic interpreter, which is why basic programs operate so slowly. Whereas with assembly language, the entire assembly language program gets converted into machine code or assembled into machine code before the machine code program even begins running. But while that assembly process is taking place, we can direct the assembler to perform some tasks for us. And we do that by giving it directives, which are called assembler directives. And each assembler that we use will have its own set of directives, although some of them are very common between different assemblers. And I've just given a few examples here on the right side. The top one is called labels. So labels are names, similar to how you would use a variable name in BASIC, for example. In assembly language, we have something called labels, which can be used to refer to either values stored in memory, which kind of get used as variables would be used in BASIC, or we can also use them to refer to particular values, which would be similar to how we assign constants in BASIC. And I'll discuss that a bit more in a moment. Now, the next point I've listed here is the org directive. So org is an actual directive you would type into your assembly language program, as shown here. In the example, I have org $4000, which is hexadecimal 4000. So this is a very important instruction to have in your program if you want to specify where in memory you want these machine code bytes to be stored once our assembly language program is converted to machine code. And this would be important if you want to make sure that your program will work when it's installed at a particular location in memory. So when we load a machine code program into our computer to execute it, we're going to be loading that machine code program into a certain location in memory. And we want to make sure that our program will actually work when it's installed at that location. So when we load our program into our computer to execute it, we want to probably make sure that the location we load it into memory matches the original org statement value that we have in our assembly language program. And of course, you can also use the org statement at different locations in your program if for some reason you want the code at that location to be stored in a particular memory address as well. So let's take a look at our next instruction here, or assembler directive, which is called EQU. So this would be an equate directive, and how this works, for example, is it's similar to assigning a constant value in BASIC. So you could assign a label to a particular value using this EQU assembler directive, and then in your program, when you're referring to a particular number, you could refer to it by its label instead of its value. And this might be important and useful for a few different reasons. So why would you want to assign a value to a label using this EQU directive, which is similar to assigning a constant in BASIC? Now keep in mind that these assembler directives only get executed during the assembly process. They don't get executed during the execution of the program itself. So we can't use an EQU instruction, for example, as part of our program to change the value of a label while the program is running. These directives don't take place while the program is running. It only takes place once during the initial assembly of the program. So we can assign a value to a label, for example, but we can only do that once. And once it's assigned a particular value, it stays at that value while our program is running. But the way this would be useful, for example, would be if you want to assign a value to a label, then you can use that label to refer to that particular value throughout your program as you're creating your program. And this would be useful for a few different reasons. Let's say, for example, you want to assign a value for the maximum number of lives a player can have in a game. And maybe you have a label called max lives. So if you assign a value to that label, max lives, let's say you assign it the value 3. And in your game, the maximum number of lives a player can have would be 3. Well, then when you're creating your program, you might find it easier to remember the label max lives instead of remembering 3. So these labels can be easier to remember than the actual numeric values, which is one reason you might want to assign values to labels using an EQU instruction. Another reason you might want to use an EQU instruction to assign values to labels would be for debugging. So when you go back to your program later, and you might not remember what all the different numeric values represent, so you might not remember that the value 3 in a particular line of your program represents the maximum number of lives the player can have in the game. But if that 3 is replaced with a label called max lives, then it makes it much easier to troubleshoot and understand what the different label names refer to. And the third reason why you might want to assign values to labels would be for easily changing that value in your program. So if you assign a value to a label using this EQU assembler directive, then instead of having to go through your entire program and replacing that value if you decide to change it, let's say, for example, you decide you want your player to be able to have 5 maximum lives instead of 3, then instead of having to go through your entire program and replacing all the instances where you use that value of 3 and replacing it with the value 5, you only have to replace it once wherever you assigned it using this EQU assembler directive. So you can see, I think, how powerful and useful this assembler directive would be for us. And then now let's go on to the third one I've listed here, which is actually 2 directives called DB and DW, which is define byte and define word. These 2 assembler directives store particular values in memory. And this is similar to how we would assign variables in BASIC. So the EQU instruction that we just took a look at, although it assigns a value to a label, that value can't be changed while the program is running. However, using these define byte and define word instructions, or assembler directives, this allows us to store values into memory locations, and of course we can change the value that's stored in memory locations as the program is running. So in this way we can use the combination of labels with these define byte and define word assembler directives to kind of act like variables, because we can actually change the values that are stored at these memory locations, which are pointed to by the labels that we assign in these instructions as well. So that's another area of knowledge that you'll need to be familiar with, is how to use assembler directives in your assembly language program. So we'll need to familiarize ourselves with the different assembler directives that are available for our particular assembler. Let's take a look at our next slide, which is titled Assembly Instructions. So this is what I mentioned before, is every processor or every CPU has its own list of assembly language instructions that it understands. And of course we need to familiarize ourselves with those different instructions and what they do and how they work. And if we take a look at the list on the right here, there are a few different aspects of those instructions that we will be interested in particularly. And the first one is called opcodes. So the term opcode is what's given to the actual assembly language instruction. So for example, here if we take a look at this left-hand chart for the Z80 microprocessor, it has an opcode called LDA. So this would be the opcode for this assembly language instruction. And these instructions are also known by mnemonics. And then the other part of the instruction that's included along with the opcodes is something called the operands. So the operands would be the values or the memory locations, etc., that would be operated on by the particular instruction or opcode. All right, let's take a look at the second point here, which says timing or T states. So I mentioned this earlier in the video as well. Each assembly language instruction has its own length of time that it takes to execute, and this is typically shown in what's called T states which are cycles. So if you have, let's say, a Z80 microprocessor that's operating at 3.5 megahertz, that's 3.5 million hertz, which is 3.5 million cycles per second, which is 3.5 million t-states per second. So each assembly language instruction is typically identified by how many timing states it takes to operate, or how many t-states it takes. And then you can use these t-states to calculate how long in real time it would take for a particular assembly language instruction to operate. In case you're interested in making your program run as quickly as possible, then you could look up the t-state value for the instructions that you're using in your program and maybe see if they can be replaced with different instructions that take fewer t-states. All right, the third point here says number of bytes. Now, if you're interested in saving memory in your assembly language program, if you want your program maybe to be as small as possible, then you can see how many bytes each assembly language instruction takes. So these two different points here, the timing of the instruction and how many bytes the instruction takes up, these are things we may not typically be looking at when we're creating a program using a higher level language such as BASIC, for example. But with a low level language such as assembly language, we can find out exactly how long each instruction takes to operate, as well as how many bytes that instruction takes up in memory. And then the final point I've listed here is the effect on flags. We don't have this consideration when programming in a high level language such as BASIC, but it's absolutely critical when programming in assembly language. So in addition to understanding how each opcode works, or how each assembly language instruction works and what it does, it's also extremely important that we understand the effect of those instructions on something called the flag register. So as you are probably aware, if you're interested in assembly language programming, there is something called a flag register, which keeps track of certain aspects of a calculation that would have been performed by the instructions in our program. So certain operations that we put in our assembly language program would have an effect on these flags, or the different bits in the flag register. And this is what we use for doing comparisons. For example, we might check the value of a 0 flag, which detects if the result of a calculation was 0. We might do a comparison on what's known as the carry flag, which detects if the result of a calculation produced a carry. And so we can check the different statuses of these different flags in the flag register in order to make our program operate the way we want it to, and particularly doing these conditional checks for branching and jumping and looping and so forth. But in order to be able to effectively use these flags, we need to understand the effect of the different assembly language instructions on those flags, and which instructions affect which flags and how they affect them. So that is a very important point that we need to learn when we're going to be programming in assembly language. All right. Our next slide here is titled Assembly Characteristics. So assembly language programming has its own set of unique characteristics that is very different from basic programming, for example. And we're going to take a look at some of them here on the screen. The top one says registers. So each microprocessor has tiny little storage locations built into the processor known as registers, and we can both check the value of those registers as well as manipulate the value of those registers, and we can transfer data back and forth between internal registers and memory locations, for example. And it's very important that we understand the characteristics of the registers in our particular microprocessor. We need to know which registers it has, how they operate, what types of values they can store, and how we can manipulate and check those values. And typically different registers would have different operations available to them. So we need to familiarize ourselves with registers when we're doing assembly language programming. Now the next point here says stack operation. Assembly language programming has something called a stack, which is a location typically in memory, which can be used for temporary storage of values when we're executing our machine language or assembly language program. So the stack is an important feature of assembly language programming to understand as well. And it's also important to understand some of the trickier operations of the stack, because it can cause bugs in our program that we might not expect. We might not, for example, necessarily understand exactly how and when the stack is being manipulated, and if it's being corrupted, for example. So we need to really pay close attention to the stack in assembly language programming to make sure that we're using it properly. Okay, our third point here says bitwise operations. So I mentioned this briefly before, how in basic programming, we typically use just decimal values, regular decimal numbers. But in assembly language programming, since we have the option of using decimal values, binary values, hexadecimal values, or some combination of all three of those, one type of operation that is available to us is bitwise operations, where we can actually manipulate the individual bits within a binary byte. So this is something that we don't typically do in BASIC, but it is available to us in assembly language. And so we need to familiarize ourselves with the bitwise operations for both checking the value of the bits within a byte, as well as manipulating them when we need to. And this can be done with individual bit operations. There can be rotate operations. There can be shift operations. There are logical operations such as AND, OR, exclusive OR. So the bitwise operations are very powerful in assembly language, so we need to familiarize ourselves with those as well. The next point here says relative jumps. So this again is different from basic programming. When we do a jump in basic programming, we typically use a go-to statement to go to a particular line number. But in assembly language programming, we also have a different action available to us, which is known as a relative jump. So instead of jumping to a particular location, which in assembly language it wouldn't be a line number, but it would be a memory location where we have some code stored that we want to execute. But we also have something known as relative jumps, where instead of jumping to that particular location by specifying it as an actual specific address, we can jump to a relative location in memory, which is an address that is referred to by an offset from our existing location in memory. So that is something unique to assembly language that doesn't appear in basic programming. Okay, our next point here says conditional checks and jumps. This would be checking a value, as I mentioned earlier, probably of one of those flag bits, doing a conditional jump based on the value of a flag bit. We would typically need to perform some sort of operation which would manipulate or affect the flag registers, and then we would do a conditional check on those flag registers, again to see if the result was 0 or if it produced a carry or whatever, and then that is how we would do a conditional check to do our jumps in assembly language. Okay, the next point here says sequence of bytes stored in registers. Since assembly language instructions and values get converted into bytes, and for example with an 8-bit computer, each memory location would store an 8-bit value or a single byte value. So what happens in assembly language is if we're using a larger value such as a 16-bit value, for example, which is a 2-byte value, well, we can't store 2 bytes in a single memory location, so we need to split up those 2 bytes into their individual bytes and store those in memory locations. And we need to understand how those bytes get stored in memory. For example, a 16-bit value or a 2-byte value would be converted into its high and low bytes, and we need to know which order those bytes get stored into the memory locations in order to be able to understand how our program is working and to be able to check those values and make sure that we have the right values in the right memory locations. And then our final note here says sequence of bytes stored in memory. So this is actually related to the previous note we just took a look at, where it says here the sequence of bytes stored in registers and the sequence of bytes stored in memory. And there's a difference between how those high and low bytes are stored in the internal registers and how those high and low bytes are stored in memory locations. And we need to be familiar with both of those. Okay, let's go on to our next slide here, which is titled Memory Map. So in basic programming, we may need to be familiar with how the memory is allocated in our computer for different purposes. And in assembly language, we definitely need to know how the memory is split up in our computer and how it's used for different purposes as well. And if we take a look at our list here, the typical personal computer will be divided into ROM memory and RAM memory. As you probably know, ROM memory is read-only memory, meaning you can read the values, but you can't adjust any of the values. You can't write to ROM memory. However, ROM memory is important because it often contains useful subroutines that we can actually access as programmers for use in our programs. And then we have RAM memory, which is memory that we can actually manipulate. And we need to understand how these different ROM and RAM types of memory are used in our particular computer. And here I've listed several different types of uses that may be applied to ROM and RAM memory in the particular computer we're looking at. And the top one here is called system variables. These are internal variables that the computer uses in order to keep track of different things it needs to know in order to operate properly. And so we need to know where these system variables are stored, both so we can access them and also to make sure that we don't overwrite them. And we need to know where our basic program is stored in memory, again, so we don't overwrite it, and also so that our basic program doesn't overwrite our machine code program if we're using a machine code program in combination with our basic program. And then the memory might also be divided into some other types of uses as shown here: video character RAM, color attribute RAM. Typically a computer will have memory allocated for the graphics shown on the screen. This could be character graphics, this could be bitmapped graphics, and it could also be the color attributes that are shown on the screen. So if there are areas of memory that are reserved for either video character graphics or bitmapped graphics or color attributes, then we need to be aware of where that memory is being stored in our computer. And our next point here, labeled assembly stack. So this is the stack we just mentioned. This typically will be stored somewhere in the RAM memory, so we need to be aware of where that stack is located in RAM, again, so we don't overwrite it, and also so the values that are stored in the stack don't overwrite our program as well. And depending on the computer you're looking at, it may have a feature known as bank switching, where you can swap out different areas of RAM into other areas of RAM. So if you're using a computer that has bank switching, then you're going to need to know where those different blocks of memory are stored so that you can effectively swap those banks in and out of active memory. Okay, so our next slide here is referring to the different aspects of the particular computer that we're using that I mentioned in the first slide, where we want to know which computer we're going to be developing our program for. So once we've chosen a computer that we want to develop for, we need to be familiar with the different aspects of that computer. And of course, this would be the same no matter what type of programming language you're using, whether it's a high-level programming language such as BASIC or low-level language such as an assembly language. We still need to familiarize ourselves with the different aspects and characteristics of the particular computer we're programming for. And this would include such things as the video display, including the characters and color attributes, the screen resolution of the computer and the different video modes it might have available, the character or bitmap display that it might have. Some computers use a character display such as the Mattel Aquarius. Other computers might use a bitmapped display such as the Sinclair Spectrum. So we need to be familiar with how the graphics and characters are displayed on our computer. And then if your computer has a sprite capability, it may have hardware or software sprites built in, so we need to be aware of that capability as well. We need to familiarize ourselves with the different ports and inputs that are available, how to read from a joystick, how to read from a keyboard. We're going to need to be familiar with the different ports required in order for us to be able to read from those different devices in our assembly language program. It's useful to familiarize ourselves with the different system variables and ROM subroutines, because we can make use of those system variables and ROM routines in our programs that we write as well. So we might want to check the value of a system variable, or we might want to manipulate the value of a system variable, or we might want to make use of a built-in ROM routine that performs a function that we are trying to perform in our program without having to reinvent the wheel and rewrite the routine ourselves. If there's an existing routine that exists in the current ROM of our computer, we might want to just take use of that existing routine. And then finally at the bottom here, that's cut off a bit, it says sound capabilities. We want to be familiar with what sound capabilities our computer has and how to make use of those. And then finally on our last screen here, it says getting started. So now that we've kind of taken a look at different aspects that we need to be familiar with when we're interested in learning to program an assembly language, how do we actually get started learning all that information? Well, let's take a look here at the list of some suggestions that I've outlined for us. The top one says YouTube videos. So if you're familiar with my YouTube channel, for example, I've covered, I think, pretty much every topic that I went through in this video in my previous videos. So if you're interested in learning more about any of the topics that we took a look at in today's video, if you go back through my previous videos, you're probably going to find a video that relates to each of them somewhere in there. So you can obviously look at my YouTube videos, and you're free, of course, to look at other people's YouTube videos. There are many YouTube videos on the internet relating to assembly language programming for your particular processor or your particular computer. So just do a search and see what you can find on YouTube. And it's always I think, very useful to find videos that show other people doing what we're trying to learn how to do. My second note here says books. Now, the great thing about learning to program for retro computers nowadays is that many of the books that were available back in the 80s are now available as free PDF downloads. So you can search for a particular book or particular type of book you're interested in, and most likely there's going to be a free version of the PDF available that covers the particular topic you're looking for. So for example, I know there are many books available for programming in Z80 assembly language for the Sinclair Spectrums, for example. That was a very popular computer, so there's lots of books available, and like I said, many of them are available as free PDF downloads. If you're interested in a more obscure computer such as the Mattel Aquarius, which wasn't successful for that very long. Well, I don't think it was really successful at all back in the day. So there aren't many books available for that, and you're probably not going to find books available for that computer. But still, if you're looking to learn how to program in assembly language, there are many assembly language resources and books available, of course. It's just finding a particular resource that applies to the particular computer you're interested in. That may or may not be more challenging to find depending on how obscure the system is that you're interested in. All right, my third point here says Facebook groups. Nowadays, Facebook has lots of groups dedicated to all sorts of different computers and different programming topics, different game development topics. And so if you're interested in learning pretty much anything about computers, more likely than not, there's probably a Facebook group that exists that's dedicated to that. And if there isn't one already, then you can always create your own group and invite people to join it and start your own discussion about that topic. My fourth point here says online resources. That's pretty obvious. Of course, today with the internet, there's all sorts of online resources. We can just Google any topic we're interested in, including assembly language programming. And then our next point here says IDE, which I mentioned stands for Integrated Development Environment. I particularly love integrated development environments because when I'm looking to get involved with a particular computer, a retro computer in my case, what I'm interested in is a computer that I can actually develop games for. And the easiest way to develop games for a retro computer is if it has an IDE, because I like to develop my games using modern hardware, a modern PC. And if there's an integrated development environment available for my PC, of course that makes it very simple to program for. And of course that combined with the other points we mentioned above, YouTube videos, books, Facebook groups, and other online resources, if all of these things are available to us for programming our particular computer or processor, then it makes it just that much easier. Okay, finally, what's next? Well, of course, what's next for you is up to you. If you think you might have any gaps in your knowledge for any of the topics that we covered in today's video, then you might want to take a look for different resources that cover areas of knowledge you might be missing and kind of brush up on that knowledge before beginning to program in assembly language. Whereas what's next for me, I think now I'm at the point where I should be able to create a game that incorporates at least some machine code into it, so I can begin making games that have maybe a combination of basic and machine code, and maybe one day work my way up to the point where I have an entire game written completely in machine code. So I think that's going to be my next challenge, is actually using the information that I've learned to making a game that incorporates at least some machine code in it. And hopefully you'll get to the point where you're ready to create a game that has some machine code as well. Alright, so there we have a look at the different considerations that we need to keep in mind, as well as the different areas of knowledge and some different tools that we need to have available when we're interested in learning to program in assembly language. And hopefully you'll find that some of my videos might be helpful in learning to program in Z80 assembly language. So feel free to go back and watch some of my previous videos if you think they might be helpful for you. Otherwise, as I mentioned, I think my plan going forward now is to hopefully try and make a game that incorporates at least some machine code based on assembly language programming as well. So as always, thanks for watching the video, and we'll see you next time.